Oh, good afternoon, PCS members and friends. Today we have a seminar by Andrus Giraldo from Korean Institute for Advanced Studies. He will be talking about master stability curves for traveling waves. And our scientific host today is Sergey Flach.
Yes, that's right.
who will present our speaker soon, I believe. Let's see.
He saw you and then he escaped. Yes.
So,
We can do it. There's
okay, let's welcome our speaker.
In the meantime.
Sergey, please.
Okay, maybe. Did you already?
Yeah.
Okay, good. So then, hi everyone. And maybe before I introduce the speaker, I want to use this opportunity to thank our anchorman, Dylan Chadesh, who was doing this job fantastically for the last N years, where N is quite a big number, if I remember correctly. And so I think we should all wish you a nice future and, in wherever new places you will go. And thank you very much for everything, but including also being the anchorman of our seminar series. Thank you. Now we have a new anchorman who is Oleg Utesov, or Tyozov, to say it correctly, who I'm sure will do also a fantastic job. And let me then come to our seminar speaker today, who is Dr. Andrus Giraldo. He did his bachelor in Colombia at the EAFIT University in Medellin. And then he moved on to New Zealand in 2012, which is practically the same time I moved there. So the world is small, apparently, after all, right? And where he did his Bachelor of Science at the University of Auckland, and then he continued with his PhD in mathematics, which he finished in 2017, working together with Bernd Krauskopf and Hinke Osinga. Then he continued to stay there as a postdoc or research fellow at the same Department of Mathematics at the University of Auckland, and worked there together with other colleagues whom I also know very well. And then in 2022, he moved to the Korea Institute for Advanced Study, where he is since a research fellow. And I saw recently a paper you put on the archive, and then this reminded me of things I did together with colleagues quite some time ago, what related things. And so we started writing back and forth, and as a result, now we have Andrus here to give us a talk. And after I checked then the Google Scholar page, I thought maybe I should have asked for also another talk, because there are lots of other interesting publications which you can find on which Andrus produced. So please have a look at them if anyone wants to chat today. He will leave at the end of this evening tonight, but Seoul is not far away, so it shouldn't be hard to get in touch again. But with that all maybe said, I should not take your time. So we are looking forward to learn news on master stability curves for traveling waves. Let's welcome our speaker.
First of all, thank you very much for Professor Flash for the invitation to talk today in your seminar. So today I'm going to talk about project that is in collaboration with Dr. Simon Rochelle. He's a research fellow from the University of Leeds in the United Kingdom. And this project is motivated by studying how waves, what are the stability of waves when they move around a particular network with certain structures. So to motivate this talk, you can imagine as an example of what we're trying to convey or achieve is that we're going to have this following setup. You're going to have nodes. You can imagine that each node will represent a neuron, and then this neuron is going to be coupled with this nearest neighbor. All right, so here I'm just presenting X1 is going to be coupled with X2, and this is gonna be coupled with X3, and so on. And then at one point, when I reach my end, my end node, this end node is gonna go back to the first one, right? So I'm gonna have like a ring-like structure. Now, as I said before, you can imagine that these nodes are neurons, and as such, you can choose how to model the dynamics inside of each neurons. Here, I'm just showing you physical-Nagomo type of equations where each internal dynamics are given by this ODE. B will represent the voltage, and here I'm just representing how these neurons are actually being coupled to each other. Now, you'll know that, for example, in applications, it's interesting to know that to understand when, for example, if I start with a pulsing solution, if that pulsing solution actually moves along this ring structure and actually is maintained under small perturbation.
So,
Yes.
so V and W are functions of X? And V and
No, X is a two-dimensional vector. I'm just representing each component as B and W. B is going to be the potential or the voltage on the neuron, and W, if you know a little bit of the physical Nagomo equation, it's just a scaling variable. All right, but in this, in principle, could be any ODE. All right, I'm just showing an example with biology.
V and W, they are not related to each other, like position on the vector or something like this?
Yes, W is related with B. So basically, each node has a two-dimensional vector, right? So you have 2 times n dimensional ODE. All right, you can see it that way. All right.
And it's not a Hamiltonian system. No?
It's not a Hamiltonian system yet. All right, but in principle, you can also apply this Hamiltonian system. Just for the techniques, then you have to add another setup.
You mentioned that V is voltage, and what is W then physically, for example, in some
All right, so
neuron system and something.
yeah, for these particular equations, it's like if you know a little bit about the history, you have the Hodgkin-Huxley model where you have voltage and 4 other variables that represent how different gradients of biomass or atoms inside or ions inside the membranes actually transport each other. Now, the physical-Nagomo equation is kind of like a conceptual model that takes the physical-Nagomo, the Hodgkin-Huxley equation, and they just try to replicate in a lower dimensional system the dynamics of this voltage, right? But as I said before, this is just an example. You don't care so much about the equations per se. This could in principle be also physical-Nagomo, Hodgkin-Huxley. Now, what I'm showing here now is like, as I said before, we're interested to understand when you have a traveling wave and when it is sustained, right? So here you can imagine that if I make, for example, n is equal to 20, here I'm just showing you the index, and I put a pulse, I start with a pulse, then you can see that the pulse is moving across my entire unit. So here I'm just showing my index, and this is my time. All right.
Sorry, once again, I'm not very familiar with this kind of model, but what's this 2 divided by 10, I don't know, 8 divided by 100 represent?
Sorry,
Was this in the system of equation?
yeah.
Why it's not 1 divided by 5? I don't know.
Well, that's
what is it?
No, that's how they created the model, right? Like this is a particular model in biology, and they use it for this kind of studies, right? So the idea is that we wanted to study this particular one because a lot of people are interested in this kind of. Well, they use this kind of model just to understand certain things about or certain properties about neurons. Again, the point is not so much about the direct equations itself. All right.
But anyway, these positive numbers, they make the zero solution unstable. So it should every time develop some kind of signals, the system. Yes.
Not necessary, and I'm going to show you an example where you don't get that. All right.
Okay.
Sure. And that's not necessarily true what you said. So I will show you later an example. All right. Now, when you want to study the stability of these particular solutions, since they are traveling waves, you can represent as periodic solutions. And in this sense, now what you want to study is basically is Floquet multipliers or is Floquet exponents, right? So if you know about Floquet theory, the Floquet exponents are the logarithms of the Floquet multiplier divided the period. For the remainder of this talk, my exponents are going to be represented by lambda m. And what you want to see if this object was actually moving stably across my network will be that the real part of all my Floquet exponent should be negative, except 1, which is my trivial Floquet exponent.
Let's see, not so fast.
That's sure.
So again, in this picture there, where you see this moving front or moving wave, so y means some what? Potential, some V, which is of the order of minus 1.5. No, white is, yes, minus 1.5, yeah?
Yeah.
And so that is the ground state? Is that some kind of like a stable background which would exist without any?
Actually, the ground state would be the zero. So you have the zero solution.
The zero solution is not white, right?
No,
Here we have something blue
white.
moving on white. And so to me, this looks more like.
Another thing. So you're saying that it just decays to minus. Yes, you could if you find the state state, you might find maybe a background. Now, for this particular problem, the tails of this periodic solution don't decay or go close nearby. So
Well, my question is what is the stable background, or kind of like what we would call a ground state, or some homogeneous solution state which will not change?
Yeah, I will have to check it here, but then if you were to make all of them equals, I guess you want to make this one zeros, but yeah, I don't have it right now really with me. But yeah, there is a state there.
And another question about this Bloquet exponent. So what you, I think you jump here over several technical details. So you evolve your dynamical system over some time.
Yeah.
Capital T, for instance.
No, T is a period of my periodic wave. So in this case, you can let T go as much as you want.
Yes, but I mean, isn't that the time your wave needs to go once around your finite system?
Yeah, that will be represented by
But
T.
there is some capital T, and then and then you compute the then you compute the eigenvalues of the Bloquet, the corresponding Bloquet matrix, which is Is that correct?
So you take the monodromy matrix, and then after you compute the monodromy matrix of your periodic solution, you find the Bloquet multipliers.
First, you find the eigenvalues, and then these eigenvalues are sitting on the unit circle or somewhere.
No, they sit in the unit circle or outside.
Inside somewhere.
It's somewhere inside.
And now you take one of these eigenvalues, and this is a mu m.
That's what will be my mu.
It's a complex number.
It's a complex number.
What means logarithm of that then?
It's a logarithm of a complex number. So
is it that, or is it the absolute value?
No. It's the logarithm of the complex number.
Just to check, is this complex number his unit norm?
No, not necessary. So if it has a unit norm, you are at a moment of a bifurcation. So your periodic solution is a moment of bifurcation. If all your mu m's are inside the unit circle, then you have a stable attracting periodic orbit, right? And when you take the logarithms of these Bloquet multipliers, then they're gonna be all sitting on the negative left-hand side of your complex plane, if you were to compute it with respect of lambda, all right? Sure. And then if you're on the unit circle, you're effectively gonna be mapped on the imaginary axis. So.
And you always have to have some which are sitting at +1 on the complex plane, right?
So if you take the Bloquet multiplier, you're always gonna have one that is called the trivial bundle, which corresponds to the solution, the direction of the flow.
That's the zero there, yeah?
Yeah, that's the zero. That's the zero Bloquet exponent that we have here. Yeah. So, and to continue a little bit with these ideas, if you have 20 nodes and then you have a two-dimensional vector, each node is represented by a two-dimensional vector, you're going to have 40 Bloquet exponents. Here I'm just showing where 20 of the 20 biggest one lie. So, and you can imagine that, now continue with the talk, if, as you can see here, this will imply that this particular traveling wave is stable. Now, you can imagine that if I have 20, I can also do the experiment with 100, and it can put 5 copies of this particular solution.
Just a sec, what is this little box there on the right?
This is a zoom of this area.
Why would you zoom that?
Just to see how they're accumulating around this. You just have a look on how they're accumulating. Now here you can also do the same experiment with 100. Now you can imagine that if you have, given that this system is symmetric because all the neurons, right, are being have the same system of equations, basically they're zeta and equivariant. you can actually buy 5 copies of this particular traveling wave, right? So you can actually do the same simulation, but instead of having 20, you have 100, and then you have 20 copies of them, all right? So mathematically, the subject would exist.
5 copies.
Sorry, 5 copies of it. And then now the question will be, all right, where are the Floquet exponents of this particular solution now in this higher dimensional embedding, right? Because you know already that in this case now we'll have 100 nodes, and I will have two-dimensional vector for each one of the internal nodes. So we'll have 200 Floquet exponents, all right? Now, if I were to draw them, and I'm drawing them here on a solid blue line, now you can see here where they accumulate, right? Now, why I'm just showing you this figure, because now you can imagine that if I were to increase this n to higher number, right, it seems that these Floquet exponents and also the Floquet multipliers have to be lying in a particular curve. So now, this curve, which I'm going to call my master stability curve, is going to be the topic of my talk. And I'm just going to basically convince you that such object exists. And not only that it exists, I can actually show you a numerical scheme that can reliably compute this without the need of, for example, having the dimension of the system. So, sorry.
When you started with n equals to 20 cases,
Yeah.
and you said that you took the largest 20 Floquet values and you plotted there, right?
Yeah.
So when you went to n equals to 100,
Yeah.
Are you taking like largest 100 or are you?
Yes, I'm putting the largest 100. So the other 100 are here, like basically more negative, like they're more negative over there, but exactly that.
I'm lost. Why only the largest, not everyone?
We can compute all of them. I'm just showing you for this presentation, just in this part, I'm just showing you the first largest ones.
And what means I'm also part of what means 0, 0 and 0, 1 there? So
I know it's 0 point, it's not showing here. So it should be here 0.0 and then here is minus 0.0, minus 0.1 and then 0.0 here.
So this is minus 0.1.
Well, that is minus 0.1, yeah. Yeah.
Sorry, just a question. So the 10 and the 100 negative ones, they have some sort of symmetry between the plus ones and the minus ones, or what?
No, there is no symmetry with so basically the two curves how they lie different to each other.
I see. So the 100, the smaller ones, they also lie on another stability curve?
Yeah, they also lie on another stability curve that we can also compute.
I see. So basically what you are saying is that the number of stability curves and all those things, that will depend on the kind of limit cycle.
Yeah, so for example, in this case, let's say as a minimal bound, if you have a if your internal dynamics are given by a d-dimensional vector, in this case 2, then you're going to start with two curves, right? But it might be the case, and I'm just going to show you maybe after that some of these curves might interact and you might have more than 2. But again, the numbers are quite small. Like it's not, we're dealing like with 100, we're still dealing with 2, with the internal dynamics of D. All right?
I'm asking because X is basically a two-dimensional object. Like you have this V and the W. So does that mean that you always are starting fundamentally with 2 stability curves? Or like you can you have a situation, for example, where you have 3 stability curves?
Yes, and I can show you the situation after. Don't worry. So we're going to talk about it. All right?
Also, that 0.1, shouldn't it be minus 0?
No, it's minus 0.1. That's what Sergey was saying. It's just, I know what topographic mistake here.
Don't worry, we will just take over time. Don't worry.
Yeah.
We will not stop you before. But I have another question.
No, sure.
It's not.
No,
it's not so. So suppose I have your 20 system with 20 sides.
Yeah.
And I have a limit cycle which is stable.
Yeah.
And then you have all the eigenvalues. Now you double the system size, or and then you argue that is still a solution of a repeated solution.
Yeah.
But it's not clear that it's still stable.
Yeah, that's a good point.
But you kind of like say, okay, this is how it looks like. You always accumulate on this curve there, so everything seems to be stable.
Yes, but maybe in this example, or maybe the message that I want to convey here is exactly that one. When you embed it into a higher one, it might become unstable. Okay. I'm going to show you some examples, but the message that I wanted to make is like these points, right, or these Floquet exponents have to lie on a curve, right? And the fact that we can compute the curve can actually tell us basically the situation of this particular traveling way in different embeddings. All right. So, but it's exactly that. And then you're going to see there is a particular example where you can see that. Now, as I said before, one of the biggest messages about my talk is like how you can first that this object exists, how would you compute it? And then I'm just gonna show you that when you set up this kind of problem, you actually don't need the dimension of your sites, and actually you are gonna end up with what is called a delay advanced differential equation. And solving the, let's say, two-point boundary problem, this delay advanced differential equation will allow us to compute these particular stability curves. And I'm gonna show you, and hopefully you're gonna get convinced that you can actually use this curve to actually get a lot of information without needing to recompute stuff in different kind of higher dimensional networks. All right. All right, so as I said before, that was an example. This is right now, I'm just gonna set up what is my mathematical framework, or the kind of mathematical system that I'm gonna be working up. I'm gonna consider a theta n equivalent network of dynamical system where I have n nodes, and each node has a d-dimensional internal dynamics. Now you can imagine that each of my nodes are given by the ODE for each node is given by this particular function, where G is basically defined over the Cartesian product of 2R plus 1 of my d-dimensional vectors to RD. You can imagine the R represent my radius of coupling. All right, so this is not necessary for my nearest coupling, right? I can have different types of coupling, and I can actually show that even the coupling can be asymmetric. So basically, you can have a stronger coupling to your following network and a weaker to my weakest one. So on. All right. What I need you to focus here is like xj is going to go exactly in the middle of my vector. This is just for representation purpose. Also, I'm going to assume that G is sufficiently smooth. All right. Examples of systems of this form, you have the physical Nagumo equation that I showed you before, but then this is something that I guess physicists see more often, where you have each node, you have your local or internal dynamics, and then you have a function that couples to each of your following networks. All right. So these type of equations can be rewritten on this form. All right. And why do we want to study this kind of system? Well, first, we want to understand how these traveling waves also behaves on this network, but you can imagine, and this naturally arises in problems with PDEs, is that you normally discretize your PDE. When you discretize your PDE, you actually end up with a lattice or a network. And the idea is, or what we want to convey is that you can use these techniques to actually study maybe the PDE or stability case system, all right? So how to derive? So we start from this is our original problem. Now, as I said before, we're interested in traveling wave solutions. So we are going to have each of my internal dynamics of my nodes are going to be basically given by a delay of a profile function. Yes, question?
Yeah, what is ZM equivariance?
Yeah, so it means that if I were to permute my my vector by a shift, like basically I just move everything to the left. So basically this becomes R minus 1, this one becomes J plus 1, and then this one becomes X over J plus R plus 1. Then you actually end up with the equation of X of J plus 1. So basically means that your system is symmetric on the permutations of labels.
You mean it's translational invariant?
It's translational invariant, all right?
Well, I mean, it's probably generalization of translation invariance to arbitrary networks.
No, this is you consider a 1D network still, right?
Yeah. So we still consider a 1D network, but then in cases when you have, for example, 2D networks where you have periodic boundary conditions, right? If you are clever under certain conditions, you can actually embed that two-dimensional lattice or n-dimensional lattice into a ring network structure, right? So what I wanted to say, and maybe we can explore it maybe after the talk, is like you could, by relabeling nodes, right, take a two-dimensional lattice in principle and actually embed it into a ring network. So, and why is that? This is kind of like a funny result in mathematics. It's like if you have, for example, a lattice where you have, for example, three nodes or three horizontal nodes and 5 horizontal and vertical nodes, you have a grid like that, and you have periodic boundary conditions, then you have a result that it will tell you that theta3, the cross product of the group acting on this space is actually C15. So you can always find an embedding. But that only happens if a number of horizontal nodes and a number of vertical nodes are actually on co-prime. to show it, but that's just more like a technical term.
Yeah, and now for pedestrians again. So this is translation invariance or not?
Yeah, well, you can make translation, but like, for the purpose of this, I mean, it's like you kind of use certain ideas like that. But anyway, we're looking for solutions of this way, and then in the position of the network, it will tell you how much of the delay you have from your traveling wave. Now YT will be our wave profile, and it's going to have minimum period T because we're assuming that this is going to be a periodic traveling wave. And because it satisfies this property, then it has to, all my x1s and xn have to satisfy this equality. And since this is a periodic solution that is traveling around my ring network, then you have, when you finish, you should actually reach the first one again, right? And this will imply what is called, let's say, this will imply a relation between my delay and basically my period in such a way that because I need to close, my tau has to be in a rational relationship with respect of my period. All right. So one of the most easy example, like if k is equals 1 over n, all right. So after I do n steps, then this will be t plus tau, t plus t. All right. So that way it will close it. All right. Now, if I have an equation like this, I can always rewrite my differential equation above as a delay advance differential equation of this form, where there is no index I anymore.
Sorry, we want some question that here the period boundary condition that you mentioned.
Yeah, this one, yeah.
It reminds me some similarity with the block wave function in just the lattice model. And here seems that there's no some phase factor due to some travel. Is there some reason why it's not shown this condition?
I'm not getting the question, so can you ask it again? Because I just wanna answer it properly.
In this solid state physics, you consider the lattice model, and you assume the form of the wave function in a block wave function, and here this prior wave function consists of the two parts, where the periodic parts without any phase factor, and then there's some phase factor due to some traveling on. But here is there some phase factor similar to?
At the moment when we're doing this derivation, we're doing it in the most general sense, so we still haven't assumed any phase yet, or phase factor yet. So let me go for it. I know quite well versed in solid state physics, so maybe when I go forward, maybe you can connect it back again and ask me the question if exactly, all right? But maybe to put it over here, or like just to make it clear, we still haven't assumed anything yet. The only thing we are assuming is like you closing itself, the second relation.
I think phase factor is just in this delay in Y function for each node.
But don't forget that these are usually nonlinear differential.
Yeah, of course, but if we linearize, then the phase factor will be just over.
No, but you don't linearize, so you have a nonlinear set of equations, so things can anyway become a bit more troublesome.
So let me continue, sorry. All right, so just to remind people, so if you have a periodic solution and you want to start instability, you need to solve what is called is Floquet multiplier or Floquet exponent problem. Here I'm just showing you the Floquet exponent problem. You linearize your set of differential equations, and you're going to end up with a problem of the following form, where you're going to have this lambda term multiplying each wj, and you're going to have the Jacobian of each of your function g at each of your components. All right. Now, because we're setting up the Floquet exponent problem, well, you need to have a Floquet multiply or a Floquet exponent of this problem. You need to find solutions of this problem such that these wj's are periodic and they are not the trivial solution. So basically, they are not the 0-0 solution, because the 0-0 solution always satisfies this differential equation. But if you find a value of lambda and wj's, which where the WJs are non-zero, then you know that lambda will be your Fock exponent. So normally that's how, when people want to study stability, you want to solve this kind of problem, all right? Now, when we want to work on this kind of traveling wave, right? Since we're dealing with a traveling wave, then we can restate the following problem now with respect of the delays and the advances. Now, now these indices will take this form. Now I'm not dealing with a, let's say, n times d dimensional OD. I'm now dealing with a d-dimensional delay advance differential equation. Now my delay has to satisfy this rational relation between this period. And now if I replace my the corresponding xj by my JT minus j tau, then I can have the problem. I'm just doing what I'm just doing here is just rewriting my system, but it's exactly equivalent to this. I'm just calling my this Jacobian matrices AM just for simplicity, so we can the indices doesn't get so confusing. And still, we still have to satisfy our boundary conditions. So basically, you have to have a periodic Fock bundle. Now, I'm showing this problem because I want to just bring a point across that the problem here on the right is normally the Fock exponent of a delay differential equation or advanced differential equation, all right? Normally, for the people who know, whenever you're dealing with the Fock exponent problem, you actually end up with a e2 minus lambda tau term here, multiplying this sum. So I'm just showing here that these problems are not equivalent. This problem is not equivalent to the delay advance problem, all right? We're still dealing with the delay, all right? So we want to find the solutions of this problem, all right? Now, this WJ, we have, so my Y's here are a d-dimensional delay advance differential equation. My WJs are also a delay advance differential equation, but then I have NJs, right? So it's NW, sorry. So it's still a high dimensional problem, so we want to reduce it. Now, if I do the following transformation, and I rewrite my WJ instead of this kind of BJs where I'm just going in an advance, then actually I can rewrite my this Fock bundle with respect of B in matricial form using the Krokener product. And where, well, this will represent the Krokener product, and C is going to basically represent how I'm coupling with my following neighbor, and C is what is called a circular matrix, right? So if you take the powers of a circular matrix, it will tell you, it gives you how you're connecting to your network. If you take the inverse, it will tell you, so C, the positive powers of C will tell you how you go backwards, how you're coupling with your backward neighbors, and the negative powers of C will tell you how you go forward, all right? The point is, like, when you write this in this form, then you can actually abuse certain results of block diagonal matrix. In particular, you can take the eigenvalues of D and you can actually linearize this particular block diagonalize this system. It's basically inspired by the work of Pecker and Carroll on synchronization of networks, where they realized that you can use this trick. And the idea is, like, if I were to do this transformation, I actually ended up with a system of equations where now my D is a diagonal matrix, which I'm doing dot product AM, and effectively each of this equation is a block diagonal matrix.
Can I ask you to go one slide back?
Yeah, sure.
To understand again.
Mm-hmm.
So in general, you would let's say have some dynamical system where you identify periodic orbit, and then you linearize the phase space flow around the orbit.
Yeah.
You consider the map onto itself over one period, and you then have to usually numerically diagonalize the problem, the matrix, to get all the eigenvalues.
Yeah.
What you say here is that your periodic orbit in your whatever 20 or 100 dimensional phase space actually is not just some periodic orbit, but has these properties that its components are
delay or advances.
Yes, there's some symmetry if you want. And then what you now say that you can also therefore transport the symmetry into the linearized phase space flow equations, right? Exactly. And therefore into the properties of the Fock matrix.
Yeah.
Okay, thank you.
Yeah, and algebraically this becomes apparent the moment that you can write it down in this form. Because here, like, you can imagine, maybe I can show it from here. when you have this expression here, your matrices depend on, let's say, delays of the tau. But after I do this transformation with the BJs, they effectively just become dependent on T. And then the dependence actually go into the B. All right, and this is an important factor because now that I have this matrix C, then I can diagonalize it. And since this matrix, it's still like the delays now are on my bundle instead of my matrix A, then I can actually effectively decouple my system. So basically, every Bj doesn't depend on Bj plus 1 or Bj minus 1, but instead it only depends on Bj and basically delays of it. All right, and this particular term that comes here is because these are the eigenvalues of my circular matrix. All right. So I'm just gonna leave a little bit here so people can absorb a little bit this. So we just diagonalize the matrix, turn into a block diagonal matrix, and because it's a block diagonal matrix, we effectively decouple. All right, and since I decouple, you can imagine that given a particular J, you have a particular bundle and a particular lambda. All right. Now, as I said before, you can embed this particular periodic way in higher and higher network, right? So you can imagine that this N can be as large as you want, right? And then J will just move between 1 to N, all right? So you can imagine that you can consider this quantity instead of being a discrete value, actually a continuous variable, a continuous value. And this is how we define our master stability equation. Now, what we're gonna study is instead of studying this problem, we're just gonna have a problem as follows. We have our delay differential equation, delay advanced differential equation, and then we have this linearized, let's say, bundle problem, which is also in delay or advance. And we have this parameter now, phi. All right. Now, when phi is a root of unity, e to the e minus phi is a root of unity, then that for a particular value of lambda, that will be a solution of my original Cloquet bundle problem. All right. So by studying the non-zero solutions of this problem, I can understand, I can map it back to the original ODE problem. All right. Again, just to summarize, we have my ODE problem that I presented before. I do the transformation, my travel wave answer. I ended up in this delay advanced differential equation. This is d-dimensional, this is d-dimensional. I still have to have my periodic boundary conditions. I need to find the values of lambda and psi that are basically non-zero. The lambdas of psi where you have non-zero solution. And if I find a value of lambda for a particular phi, where e to the I phi is a root of unity, then I can map it back to my original problem. So I actually go a Cloquet multiplier. All right. Sorry, a Cloquet exponent. All right. Now, why is this important? Because now you can imagine that you can set up, now that this is a continuous parameter, you can use actually continuation algorithms based on a Keller-Arklin step, set up a two-point boundary problem, and actually given a particular solution of this problem, for example, the trivial solution that you know it has to be satisfied, then you can do continuation on phi, and whenever phi is of the form 2 pi over n, then that will correspond to a Cloquet exponent of my problem for a variation of lambda. All right. And just to make it a little bit more concrete, this is basically what I'm trying to say. You are going to have the following two-point boundary problem, delay advanced differential equation, linearized system as I showed before. You have to have my periodic boundary conditions. Here I'm rescaling my flow by t, so that's why I'm just making my period is 1 in this particular setup. For the people who know about continuation step, that doesn't come new. For people who doesn't know, this is basically what is called a phase condition. This will be a zeta. There's a mistake. This should be a zeta. And basically, this condition makes sure that given a periodic solution, if I do a continuation in a parameter, my periodic solution is not going to stay in place and rotate. All right, because a periodic solution and its rotations are actually a solution of the first 4 conditions. The second one is a phase condition on the first component of my bundle because we are dealing with complex numbers. And here I'm just making sure that my bundle is non-zero. So I'm always rescaling to be the norm to be 1 over t square root of t. Now,
Sorry, so if you go back one slide.
Yes.
So as far as I understand, you have, when you're talking about periodic solutions, you are talking about, like, you have two sort of periods, roughly speaking. One is period in time, and the other one is this periodic boundary condition, which is this trivial, which results in this circular matrix that you have. And for that condition, this tau is equal to KT. And that results in this kind of, then you diagonalize this thing, and then that results in this stability equation. But in your network, you can have different types of periodic solutions or different types of limit cycles, say, for example. And those different types of limit cycle, like that information will be encoded in this matrix A, right? Yes, because these are basically the Jacobians of. Because you have to linearize around that limit cycle. Yeah. So now my question is that A, you have to obtain numerical, or can you obtain that? Or so. Well, there may be certain problems where you can find it analytically, but I guess those problems tend to be easier and not basically what people are mostly interested in. But normally you solve them numerically, right? Right. So when you are using this continuous equation, this master stability equation, then you put this A by hand, like, you calculate this A from your network somehow using the particular limit cycle, and then you put it in, or how? All right, so how will be the setup? Are you well versed with continuation techniques, or like numerical continuation? Okay. No, I'm asking, are you well versed or not? All right. So normally what you do here is like you discretize this equation, you discretize the linear operator, right? Okay. So you assume that Y is given by a particular discretization projection, the one that you prefer, right? So you can rewrite all these equations as a zero problem, all right? Now, what problem, sorry? As a zero problem of a finite dimensional equation, all right? Now instead of having Y, you're gonna have coefficients, right? But it's still gonna be a finite dimensional problem, all right? Now, these AN are actually the partial derivatives of your function G. So you just take your function G and you just find your partial derivatives, all right? No, but these partial derivatives, you again have to calculate with respect of time. With respect to time, but like, your X will be this original limit cycle around which you are. Linearizing, So that's why when you set up the problem, right, you are actually setting up together. You have to be the two of them. So for example, if this varies, right, this also has to vary, all right? Like what I mean, if you were to change the size of your system, or for example, a parameter of your system, you normally, since again, you are discretizing this problem whenever there's a variation here, there's also a variation here. But in principle, if you have Y numerically and you have this discretization, you can just put it out here automatically. Yeah, so what I'm not understanding is that, so you had your original network problem, which was discrete. Right? And then you have a limit cycle, and then you can numerically calculate all the Fouquet exponents the way Sergey described. So what I'm not understanding maybe just is that when you write this continuous version of your stability equation, what do you gain? Because it seems like you wrote your stability equation, then you go back and discretize it again. No. So that's a point. Yeah, that's a point. It's a good point. But let me put it this way: when you do this, right? And again, just to bring the point, you have a periodic solution, you have an error of 20, you complete the Fouquet exponent, all right? So I tell you after, I know your supervisor or you want to do the same example, but with 100. So what you do, you simulate again, you do 100, all right? Then one day it's like, no, I want 1,000. So you do 1,000, right? And then you simulate and you do it again, right? This problem, what I'm trying to say here is like, if you're studying this way, now you have a d-dimensional vector, all right? And then the question is like, now that if you treat phi as a parameter in a continuation, you can use numerical techniques that are well established, that if you get the curve, you already know where all these kind of embeddings are. So now you just treat your dimension as like one input, and that's the way it's not even like the dimension is not even an input, all right? You're just treating phi as a parameter, and whenever phi is of the form 2 pi over n, well, times L, right, is a, well, you're like, e to the I phi is a root of unity, all right? Then that problem for a given lambda, that will give you the lambda for your Fouquet exponent, all right? So in a way, now I don't have the dimension in my system, right? And that will give me a lot of versatility on what I can do after, all right? Sure. All right. So, and yes, at the end, you have to discretize numerically this problem, but this discretization will be independent of the size of your network. And that's the point, all right?
if you put in a computer.
So essentially, in other words, you are setting up your problem for an infinite dimensional network.
You can imagine like that way.
Yeah.
You can imagine like that.
Like, okay, so.
You can imagine exactly like that, right? I'm setting up that one. And since I have this 2-point boundary problem, right, I just, and by the theory of 2-point boundary problem, if you're gonna do continuation, you need to vary 2 parameters given the number of initial conditions that you have, 4. So in this case, I'm gonna vary my phi. And as I move phi, obviously the real and imaginary part of my proc exponent has to vary, and then my period is actually added as part of my continuation, but this one is not gonna change if I'm not changing any parameters. And this is how I construct this curve, right? So basically I take for example, the trivial bundle, which I know it exists. I just reconstruct these delays. I just put this matrix M, and then I just set up, let's say on DDB2, which is a package to do continuation. And I can just in one sweep, get the entire curve. All right. And then when the curve, whenever phi is of the form 2 pi j over n, then I can mark these points as the Floquet exponent of the corresponding Floquet problem. All right. I'm not doing no Floquet problem. All right.
So in some sense, this implies that for any system size you want, properties will be the same. Some universal properties.
Yeah, there's an universal. In this particular case, stability doesn't depend on the size. Right? For this particular case, all right. But I'm going to show you a case where it's not necessarily the case, all right. But you can imagine now you can cite these problems in a more systematic way, right? Now you don't think about particular size, you're talking about the family, all right? And the family has to satisfy something. Now I'm going back to the example of the Fisk-Gunagum equation again. I'm just doing this as an example. I'm again gonna do this continuation. I start from my trivial bundle. And now I can do the following. Instead of computing the curve by continuation, right, I can change a parameter in my system. In this case, I can change, for example, my delay. All right. So you imagine before in the case that I was working or I was trying to exemplify before, my delay divided by t was 1/20. That was my rational expression. That's why I couldn't embed it in a 20 network, right? But then I can actually, because tau now is a continuous variable, also you can imagine that this doesn't capture like this is, let's say, independent now from my network, right? If I do a variation in tau, right, this will change my periodic solution, but then also it will change on which kind of families I can embed the particular solution, right? So for example, here I'm just showing you that if I were to do a continuation in tau and letting these parameters to vary, I have, let's say in one continuation row, run, for example, a curve of periodic solutions. And whenever, for example, one of them is of the 1/n, then I can embed that particular periodic solution in a network with minimum dimension n. All right. So here, and this is an example where I just take, for example, when I take a particular periodic solution that I can embed in a network of 15, another one where I can embed in one in 20, and another one where I can embed in one with 30 at least. And I'm just showing here the stability curves, right? And this is something related to what we were discussing before. You can see that the one where you have 15, the curve actually becomes positive, all right? So you know already that this particular embedding will become stable, all right? And indeed, if I were to simulate, now this is my index and this is time. If I were to simulate my traveling wave with a network of 15 and I start with one pulse, I'm gonna start and then at one point I'm gonna decay. So basically my particular pulse is now sustained, all right? Now, the nice thing about this object is like now you can imagine that since 60 is divisible by 30, by 20 and 15, then all these periodic solutions that I'm showing you here should appear in the network of 60. All right. Now, for the 130 will be 2 copies of it. For the 120 will be 3, and then for the 115 will be 4 copies of it. Now, what I'm showing you here is like in the 60 network, if I were to start with the 4 copies, 4 copies of K3. So you start with this pulse. Since it's unstable, again, this object is unstable. If I let it simulate, he kind of misses the equation of attraction of the one that only has 2 pulses, but then somehow it goes to the one that has 2 pulses. All right, so basically K4. And we know that K4 should be stable because if we do the stability curve, you can see that the curve is let's say the minimum curve of the the master stability curve that is closest to the imaginary axis is actually bounded away from them, is negative in the is real part, all right? So in a way, by just doing a continuation run that can take only like 2 or 3 minutes, right? You can already get information on the higher band without needing of simulating again, all right? Now, and this is just to show more of the strengths of this approach, is that now you can imagine that I can do the same example with this continuation in tau, and then just see where these particular solutions kind of become limiting, all right? Here I'm just showing you the situation where I put it in a network where you have, if I recall, 50. Yeah, 50. In this particular setup, you can, and this is also related to a question that was done before, I have the situation where if I put it, this is the master stability curve for the wave where 1/k is equals to 50, 1/50. In the 50 network, the traveling wave or the pulse solution is gonna be stable. However, you can see that the curve goes positive. So whenever I'm embedded in the one that is 100, right, then I'm gonna have a Fourier multiplier that is gonna be have a positive real part, so it's unstable, right? And in fact, if you do the simulations, right, you're gonna see that if you start with 2 equidistant pulses, actually they start getting equidistant, all right? So here it doesn't seem that clearly, but then when I compute this, if I continue this particular Charney profile with 2 pulse solutions and I continue for a higher network, then you can see that if I put it, for example, this in a 200 network, now you can see that you have 2 non-equidistant pulses, right? So if I were to put 2 pulses in this network, they actually ended up being together. They're actually getting together. And that's the same situation. Now, this is the same situation if I put 1 pulse. So here it seems that it's stable. However, if you see this is for C2, you see this master stability curve, you can see right away that one of the Fourier multipliers is actually positive. It's just really small. So eventually, when t goes to infinity, this particular solution will actually converge to D1. All right. Now, what I have shown you right now is just basically a framework to cite this kind of particular problems on traveling waves. Maybe the main message that I wanted to convey is like by using this kind of continuation techniques and not only that, using this kind of forward and delay formulation of this kind of Loquet problem, you can actually have a framework where you can understand the stability of this wave in different kind of limiting behavior, right? In fact, one of the situations that I was showing you here, you can see here, if I do the continuation, you can see that k reaches 0. So basically I have a situation where t goes to infinity, all right? And k is fine. And this in particular case, tau is actually finite. And this will basically the case of like an approximate case of the infinite lattice, right? Where instead of having a ring network, I have an infinite lattice.
And just 1 pulse on it.
This curve will be for 1 pulse, but then this one will be for the 2 pulse, the 2 bounded pulse. So what I mean by 2 bounded pulses is like the 2 pulses are they're close together with respect to the domain, right? So basically something like this, right? These 2 pulses will be there, right? And in fact, you can imagine that this particular pulse comes as a periodic bifurcation of this 1 pulse at 1 point. And this is something that we can trace down, all right? Obviously, this is a general setup. I'm just showing you an example with a neural model because I think it's an easy way to motivate this problem. However, this can be applied in any kind of network which has the particular properties that I showed you before. An example, you can imagine that you can have a photonic crystal. I'm just showing you here a photonic crystal here, and where you have 2 defects. Now, if you were to pump light in this photonic crystal, light is going to be trapping the defects, and they're going to actually behave as a photonic resonator, right? Now, if you take a semi-classical approach and you derive the ODEs that describe the amount of light on each of these cavity, you can show that for certain parameter values, you have periodic solutions of this form, right? And these periodic solutions are traveling wave solutions. It just happens that my network is just 2. It's just 2 nodes, right? But then you can see where here I'm just showing the amplitude of one of the cavities. This is B, this is the amplitude of A. And then you can imagine that as I showed you here, when A is B, like say has it's light, like has a lot of light, B is nearly 0, then it swaps back, it's kind of like a beating sum, right? But this is a traveling wave, it's a minimal trivial traveling wave in a sense. So you can imagine you can apply these techniques. Now, to a generalization of this setup where you don't have two defects, but you can have n defects in a circle, and then you want to study, for example, pulsing solutions along this particular experimental device, optical device. Again, this is, I just show you the derivations. If you want or are more interested to see how everything goes together, let's say with more comp, well, we have a preprint where you can see everything that I've shown and basically how all the derivations follow up. And not only that, I also have the code that generate all the data from this particular presentation and also our manuscript. So if you are interested to see how these techniques are applied and you want to play with them, you can actually download the particular package. All right. So you're welcome to use it. And if you have any questions, just feel free to send a message to Stefan or me. All right. Thank you very much.
Okay, thank you, Andrus, for this nice talk. Questions?
My question. So, can you also study, because you are using this K belongs to, K can be any fraction, right?
Yeah.
In that this thing. So can you study stability for the periodic orbits also or no?
So the setup here is the stability of a periodic solution. All right. So if you have quasi-periodic, you don't have quasi-periodicity, right? Yeah, because it's periodic, right? However, yeah, let's say that you have a setup where you know that your solution is quasi-periodic, right? Then most probably comes from a torus bifurcation of a periodic solution, right? So one way to understand them in principle will be seeing how, for example, this curve is moving, all right? So the moment that this curve moves to the imaginary axis, if they come as a complex conjugate, it will indicate you that torus bifurcation might be nearby. So one way to cite this independently even of the network side is just by citing how this curve is actually moving, right? Because it gave you information about bifurcations. Yeah, bifurcations of a family of networks, right? It's not only one.
Yeah, no, that was another question I was going to ask. That start by looking at this movement of this stability curve. So other than this torus bifurcation, what other kinds of bifurcation maybe can you?
No, like all the bifurcations should actually be captured by this particular setup, because whenever you have a bifurcation, your flow K multipliers are going through the unit circle, and that will imply that your flow K exponents are crossing the imaginary axis. So if one particular bifurcation occurs, then this curve has to cross the imaginary axis. So the moment that you see a crossing, right, you know already that a particular network at that particular point is exhibiting a bifurcation.
Right. So for example, if I have a period doubling sort of bifurcation, there should be 2 points.
Yeah, it should be here on top.
Oh, here and down.
Okay. Yeah, down because of symmetry, right? Because you are taking the logarithm, right? So the moment they go fine.
2 points separate that are.
It's not 2 points. Whenever you have a period doubling, you have one of your flow K multipliers going to -1, right? It's not that you go 2, right? The issue with this representation is because I take in the logarithm, there is a correspondence between going minus pi to in the imaginary side to minus pi, right? This picture actually repeats itself every, let's say, here to pi to 3 pi, right? You have the same figure, right? So not and the same bottom one, right? So it's just that you have 2 points, but those 2 points actually represent 1 in that particular setup. All right.
So this study assumes that you actually have a dynamical system which is finite with some boundary conditions, which does allow for these traveling wave solutions. So you assume that they exist, or
yeah?
How do you know actually the?
Yeah, that's a good question, right? So how in principle would you compute your starting point? All right. So normally, and this is the issue with this kind of theoretical results, like whenever you cite the theory of equivariance dynamical system, it only tells you that periodic solution exists or might exist. Or like it just tells you what are the restrictions that periodic solution might have. Now, for this particular case, what we do is like we start from the delayed equation or the advanced, right? And we do continuation and we just find where the Hopf application occurs from a steady state. So we start from the steady state, from the background solution, the steady state. We start from that steady state, we found where a hop application comes, and then by doing continuation, right, we can just set it up in a particular setup. That's one way of doing it. Another one is like you start with a minimal network. You just simulate. If you find your periodic solution, you can just chop it up with your OD45 and you just put it in the software. That's another way to do it. So there is a lot of versatility on how you can start this algorithm in a way. You only need to start a particular starting point, but if a periodic solution exists, even let's say you want to work in a network with, let's say 20, right? But then you simulate in one of 5 because you know that the 5 has a periodic solution, that you just do continuation to the 20 after. So
one point is that technically, if I work with a partial differential equation, then if I discretize that in space, then I will get same setup as you are getting in the.
Well, yeah, your diffusion of, like say that you have a second derivative in space, right? You're gonna have your diffusion operator is gonna become an xi plus y minus 2xi. Yeah, so in theory you could use them in principle. Now, the idea is like with these techniques, right? You talk about when you have periodic boundary condition. However, if you have an infinite lattice, then the question is like, how much this can be translated to. This is a work in progress, but one of our intuition tell us that if you see this limit, right, when your period grows to infinity, right, this is the same as your boundary conditions are being pushed to infinity, right? So in certain way, these curves should capture somehow the stability on this particular case, or at least a fraction of the stability of this space, right? At least the essential spectrum.
No, maybe what I was thinking about is, let's say that you have a finite dimensional system, not an infinite, like not an open boundary kind of setup, just a finite block.
All right.
Where I have some, like, some size, like some length in the x direction, some length in the y direction. And then using this, maybe you can, or is it possible, for example, to think about a situation where you have a certain solution which is stable in 2 dimensions, but loses stability somehow in 3 dimensions or something like this?
Well, yeah, but that would be basically case by case, right? Because now you have to first see actually the dynamics of your system. These are nonlinear problems, right? I'm dealing with nonlinear problems, right? So it can, depending on your actual equations, you might or might not lose this stability. Now, how to cook an example like that? That's also an interesting question, right? Really interesting question. Now the question is like how to set it up. That's another one. But you could, in principle, think about how to cook it, right? And again, even for the cases where you have periodic lattices or periodic grids or even cubes, right? There are ways for you, depending on certain properties of your traveling wave, you can actually find an enumeration, and that enumeration can actually map it back to the ring solution. So let's say even the higher dimensional setting in certain cases can be tackled by this problem for certain particular periodic solutions.
More questions? If that's not the case, then let's thank Andrus again. Thank you very much. And I think we will have some food ready maybe in half an hour or so. So please check the lunch.
Experiment. In the experiment.
Which one?